Assalamu alaikum. Here is a question on curved linear motion. Given the van traveled over the hill described by this curve, if its speed is constant at 75 feet per second, determine the x and y components of the van's velocity and acceleration when x equal 50. So all calculations here will be done at x equal 50. Before you start here, let me remind you that x dot is the velocity in the x direction, and y dot is the velocity in the y direction, and x double dot is the acceleration in the x, and y double dot is the acceleration in the y. Okay, to start, I'm going to take the time derivative of this. Since this is given in feet, so the time derivative here will be obtained using the chain rule. We have to use the chain rule because here this is not a function of time, right? But we know that there's time here. So now here, using the chain rule, for the left side would be simply just y dot. The right side, negative 1.5 times 10, negative 3. Right, now for x squared, the time derivative for that would be 2x x dot. Okay, so this is simply 2x x dot. And if I simplify that a little bit, it would be, this is negative 0.003 x x dot. Okay, so now this is the result. I'm going to keep it for now. Okay, now since I would like to find y dot and x dot, right, at x50, so let me now replace this x by 50, right? I'm doing my velocity calculations at 50. So now y dot here will be, so I have this, right, times 50, so negative 0.03 times 50, I'll get negative 0.15. So negative 0.15 x dot. So I have two unknowns here. How can we relate them? Given in the question that the speed is constant at 75. So 75 here is the magnitude of these two velocities, of the x and the y, right? So now if you do this, let me do it here. On this side, I'll have 75 square equal x dot plus y dot square, each one. And replacing y dot from here, and we can solve for x dot. So we'll have one unknown, so this would be simply 75 square equal x dot square plus, now if I square this side, I mean the negative 0.15, I will have 0.0225 x dot square. Okay, I'll just solve for x dot, then we can solve for y dot as well. So now here, x dot, get this answer, it is 74.17, right, feet per second. You know, here we can, since this car is going to the left here, I can take this y here positive and this x to the left to be positive. Okay, so that's x dot, and here now we can find y dot. I found that to be negative 11.12, okay, feet per second. Okay, let me just fix that a little bit. Negative 11.12. Okay, so these are the x and y components for the velocity. Now for the acceleration here, let me start by this now. I have, y dot equal this expression. Now let me take the time derivative for that, right? Then I'm going to substitute x by 50. Okay, so let me now remove this. I no longer need it, right? So let me start from here. But now here we have to be careful about something important. On the left side of this here, we have two functions multiplied by each other, the x and the x dot, right? So here we have to use the product rule of differentiation. And of course the chain rule, because this x here is not in time, right? So remember that. Okay, so using now the left side would be simply y double dot equal the right side negative 0.003, just a constant. I'm going to open a bracket because I have the product rule. And the product rule now here, x and x dot, I'm going to just leave x as it is for now, x, and take the derivative for the second function, which will be x double dot, right, plus, now take the derivative for the first one, which is x dot, and I already have x dot, so it would be x dot squared. Okay, so that's now my function for the acceleration. Now I'll just replace x by 50 in this because I am interested to find the acceleration at 50 feet. And now let me just do that and do some simplifications, right? So I'll give you here, I got here, this is to be negative 0.15 x double dot plus 16.50. Okay, so that's y dot, the y double dot, I mean. Okay, okay, now how can we relate both of these, the y double dot and x double dot? Now the speed given to be 75, but does it mean that the acceleration is 0? I mean, does the car has acceleration at all, or it's simply 0? Now, since we are moving along a curve, we have to resolve the acceleration here into its components, into the tangential component and the normal component, right? And what do I mean by this? Let me just here. Now this car is going this way, right? So that is the t-axis. This is the t component, right? And this car here, for the normal axis, it's simply toward, you know, toward the radius of curvature. So this is the n. So this is the n axis, right? And you know, here somewhere we have, you know, my radius of curvature, rho, which is not given. So here also we have to think about that. Okay, now here also, you know, I can say that is my y-axis and that is the x-axis. Okay, and if I extend this a little bit here, this is the negative x here, and this is the negative y. Okay, okay. Now, since we are moving again along a curve, the acceleration for this car is like this: a equals the tangential component at along the unit vector t hat plus an along the unit vector u hat for n. Okay, now at in this question is 0, right? But an is not 0. In fact, an is equal to the v square over rho. Okay, now let us think about this. I want to find an, right? V is given to be 75, but what about rho? If the path function is described by a curve like this, right, then rho can be found from this relation. Rho equal, open a bracket, 1 plus y prime square, everything power 3 over 2, over the absolute value of the y double prime. And here we need to take the just the normal derivative of the y, just with respect to its function, with x, with respect to its variable, sorry. In this case, it's x, right? Okay, so now earlier we have found, I found now y prime. It will be now negative 1.5. Sorry, I mean earlier I found y dot, right? But now this y prime just with respect to x, it will be negative 1.5 times 10 power negative 3, right? Just times 2x. There's no x dot here, right? Because this is simply derivative with respect to time, with respect to the position. And y double prime would be negative 1.5 times 10 power negative 3 times 2. And now I want to find this rho at 50. right? So replace these x's by 50, right? And do, you know, raise this to the power and so on. So now I'll have this 1 plus, I got here the result, 1 plus a negative 0.15 squared, everything raised to the power 3 over 2, okay, over the absolute value of this. So it is simply some absolute value of negative 0.003. Okay, so here the answer I got for rho is 344.64 feet. Okay, so now that's my radius of curvature. Now let me come back to this formula here to find AN. Okay, so this will be equal, so I'm going to come back here, equal to 75 square over 344.64. Okay, I got the answer here to be 16.29 to 4 significant numbers, feet per second squared. Okay, so now that is AN, and you know, since AT is 0, this also, you know, this is the magnitude of the acceleration. So here I can say that the magnitude of the acceleration is simply 16.29 feet per second squared, right? But I'm interested to find, you know, the x and the y components. Now to do that, we need to resolve this component of the acceleration, right? So this one here, so that's my AN, right? I need to resolve that into its x and y components. The only problem I have is I don't have the angle, right? Now how can we do that? To do that, we just need to remember something important and elementary. You know, the tangent of the line is the slope of the function, right? And the slope simply is the first derivative. So now I can see, right, that the tan of the line, so the tangent of the line simply is the slope, and the slope is the derivative. And you know what? I have y, so I can just find the derivative here, and I'm doing this derivative at what? At x equal 50. Yeah. So now if I do that, I will have the tangent tan theta equal negative 1.5 times 10 power minus 3 times 2 times 50. Okay, then now I'll take the inverse to find theta. Theta here I found it to be negative 8.531. Okay, so that's theta we found here, this value. Now since I have theta, we are done almost. Let me just here free some space. We just free here this space here. Okay, I no longer need this. Okay, so now AX here simply is the acceleration, the magnitude we have found, times what now? Think about this, that's my angle theta here. Because now the slope of the curve here, the curve is sloped here. So that's theta here, right? And if I extend the line a little bit here, right? Somewhere like this here, that's also my theta. So also this is theta. So we can use any one just to find this. So it will be A for the x here. I have A sine. Now I'm using this here. So again, we just clarify this. That's AN here, and that's AX, and that's AY. Okay, so I'm saying now that's the theta here, which is we have found negative 8.531. So A times sine, let me just replace this at once. A, we have found it to be 16.29 times sine negative 8.531, and AY simply 16.29 cosine negative 8.531. So the first one here I got to be negative 2.42 feet per second square, and AY simply I got to be 16.1 meter per second square. Okay, so it means this car is decelerating for the X, and for the Y here, the component for the acceleration is here. Okay, so that's it for this video. If you find it useful, please like and share the video and subscribe to the channel, and also let us know if you have questions or suggestions in the comment. Wishing you all a good luck. Thank you.